We move on to problem 7. And you see here in this picture, you've got a large circle. And inside the large circle, you've got 4 smaller circles. And they all are touching each other, as you can see. And the question is, what is the ratio of the sum of the areas of the 4 smaller circles to the area of the larger one? Right, so here, this is a problem on area, and the question is, what is the ratio? Let's just understand that. What is the ratio of the sum of the areas of the 4 smaller circles? Let's just unpack that one. So if we know the radius of the smaller circle, okay, suppose it's the radius of the smaller circle is r. So if you know that the radius is r, then the area of the smaller circle is pi r squared. That's the area of a circle of radius r. But you've got 4 of them. So the total area is 4 pi r squared. So you need to work out the ratio of the sum of the areas of the 4 smaller circles. So in other words, you've got the ratio of 4 pi r squared. Sorry. So you need to work out the ratio of 4 pi r squared ratio to the ratio to the area of the largest circle. So the area of a circle is pi r squared, but you don't know what the largest circle is. So you need to put down 4 pi r squared like that. So the only question is now, what is capital R? What is the radius of the large circle? So that is what we need to calculate. If we know the areas, the radius of the smaller circle, is it possible to get the area of the larger circle? Right. And to do that, you have to somehow get the larger circle. Now, if I take a point of contact here, and I want to get the radius of the larger circle, I'll join it to this. I wouldn't be able to do much there, but I can go on to that. So that becomes the area, the ratio, the diameter of the larger circle. Right. Now, what do we need to do is, we've got 4 small circles. So let's just join these 4 centers. You can see quite clearly the 4 centers, if you join them, you're going to get a square with the symmetry of this. Actually, the reason why you get a square is because this is the radius of the small circle. So there is r, there is also r, r, r. So you see, this circle here is actually a rhombus because its 4 sides are equal. So it's a rhombus. But it's generally a rhombus, I mean, it's a diamond shape. And you have one diagonal is longer than the other diagonal. Generally, I'm sorry, yeah, in a rhombus. But in this case here, you'll see that the diagonals are actually equal. So it means that this is a very special kind of a rhombus. And it turns out that this is actually a square. So this distance from here to here is what we need to calculate. Let's call the center here A, call the center B. And then now you got a square here, you see? You got a square. And as I told you, the square has got lots of properties. But we need to calculate, see, this part here is R, and this part here is R also. So the diameter that we're looking for, 2R. The radius of the large circle is capital R. We gave that name to that. 2R will be the diameter of this whole thing. The diameter, you see, is going to be equal to an R here, another R here at the other end. And then you got this in-between piece here. But this is a distance between two centers. But if you look carefully, you'll see that it's actually the hypotenuse of a known right angle triangle. So AB is the hypotenuse of the right angle triangle. So that is square root of that squared plus that squared. Now this is 2R. And you square 2R, you get 4R squared plus another 4R squared on this side. And the square root of that is the hypotenuse. So here you can see this is 2R plus square root of 8R squared. And that is 2R plus, here you can take out, this is 4R squared times 2. And the square root of 4R squared is 2R, because 2R multiplied by 2R gives you 4R. So the square root of 4R squared is 2R, and you're still left with square root of 2. See, this is 2 times 4R squared. And when you work out the square root of that, square root of 2 times the square root of 4R squared, and that is what you get. And that is twice R. Right? So R itself, you can divide right throughout by 2, and you'll get R plus R root 2, or which is the same as R into 1 plus square root of 2. All right, so the ratio that we're looking for is this, and the ratio is nothing else but the fraction. It's 4 pi R squared, 4 pi R squared over pi, and this is your capital R, small r, capital R squared is R times this, so square both of them, R squared into 1 plus square root of 2 all squared. Happily, the 4 pi's cancel, the R squared cancel. And in the numerator, you just have 4. The denominator, when you expand this, you get 3 root 3 plus 2 root 2. So that is the ratio that is required. The ratio of the sum of the areas over the area of the entire circle. Okay. So here is the full solution. It certainly beats that rather scrappy solution that I gave you, written all over the place. And if you want to write this proof out, this is how you would write this thing out. So please study this carefully. Try to do it on your own first, and then look at the solution and correct yourself. But you remember, geometry, it's a story. So you have to be very, very systematic the way you tell your story. Okay, we move on to the next question. Here, you got a square. Each side of the square has got length 17 centimeters. So it's given that the length of the square, or the length of the side of the square, is 17, which means that this is 17. Now, it's divided into 4 equal parts, so that all these are equal. And you can put a single stroke here, also because the same 17 is divided into 4 equal parts. It's a square, so the sides are equal. Okay. Now, let's say find the area of the shaded region in square centimeters. All right, so how do we go around finding the area of this thing here? The whole thing is like slanted. You've got a lot of small squares here. Okay, let's see what exactly is going on. We need to find the area of the shaded region. So let's take any one of these small squares and say that the side is x, right? Which means that this area of that small square is x squared, and the shaded area, this is what we need to work out. The area of the shaded region is 4x squared, because each square has got area x squared. So we need to calculate 4x squared. So how do we do that? Okay, now watch here, quite nice. If you look at this little triangle here, you've got, this is the midpoint from here to here, and this is parallel to this. So therefore, these are equal by the converse of the midpoint theorem. Right? We used this before, I'm using it again. Now, how do we know that these two are parallel? Well, the reason why they are parallel is we've done something similar before. This is a quarter of the side, that is a quarter of the side. So these two are equal, and they are also parallel because they are opposite sides of a square. So therefore, this figure here is a parallelogram, and therefore the opposite sides are parallel. So those are parallel, and that's exactly what we used here. These are parallel, therefore these must be equal. All right. So likewise, you have all these are equal, and now again, you see this part here will be equal also. This triangle is identical with that. So this is x itself. So now how do we calculate x? We need to calculate 4x squared. But now in this picture here, you see you've got a right angle triangle. And one side is x, and the other side is 4x. So if you use Pythagoras, you'll have that x squared, that squared, plus the other side squared is equal to 17 squared. That's the hypotenuse of this triangle. Okay, and here you get 16x squared is equal to plus x squared. So you get 17x squared equals 17 squared. Okay, so that's nice. The 17 can cancel. And you have x squared is equal to 17. But we needed to work out not x, but 4x squared. So therefore, 4x squared is the area of the shaded region. That's what we needed to calculate. We know that x squared is equal to 17. So this is 4 times 17, which is 68. And that is the answer to this question. And this is the last one that we are going to do. So we'll now close up. Okay, thank you very much for listening. And I do hope that you continue to work out problems in geometry. It's a very creative subject. And when you get the solution to a particular problem, it's exhilarating. It's very fulfilling and enjoyable. So please enjoy geometry, and you will have other problems to solve in your session. Thank you for listening.